Lesson 7-1, Dilations. When this lesson starts out, it starts by asking you a couple questions based on the Roosevelt High insignia or sticker decals. So look at the relationships between this larger one and these smaller ones, and you're going to answer some questions about them. Example 1 is actually a dilation. So how can you dilate an image? I love this example because it actually goes through step by step the different types of dilations. So there are two methods. The first method is the ratio method. And honestly, it depends on your teacher whether you have to know which is the ratio and which is the parallel method. But talk to your teacher, ask what they would prefer, or if they even want to differentiate the difference. So to dilate a figure, now keep in mind, a dilation is literally that. It's making something bigger or smaller. The key is that it still looks like the original figure. So if you had a photocopy, for example, and you shrunk it or enlarged it, it still looks like the original, but it's just enlarged or decreased in size. So that's what a dilation is. And so if we had this triangle ABC and we want to reduce it by a scale factor of 1/2, notice I know that A prime with that little tick mark, B prime and C prime is the new figure. It's half as big. So you have a point of dilation, you connect it to all the original points with segments or lines, and then you cut the distance in half. So the distance from P to B cut in half is P to B prime. And it goes through it step by step for you, and you can go through this example yourself on the interactive textbook. Here's method 2, the parallel method. I'd already mentioned it. So same idea, but now you're going to take it, and this one, it says method 2, do this, make it a different size. So it doesn't really say what size, it just says different from the pre-image. So it looks like they did a power of 2 right here. 2 times as big. So again, you start at that point of dilation, point Q, and work your way outward. So the distance from Q to W, that's like considered 1. And then W to W prime is another 1. So that's a distance of 2. And notice these lines, W prime, X prime, are parallel to W, X. And that's why it's called the parallel method. And again, it talks about it right here, step by step. So if you have time or if your teacher permits, then you can use the ratio method to actually do this. If I was in person, I would have my students do it with a compass. But you might be able to do this on the computer program. So ask your teacher. Again, another version, just with the parallel method 1/3. So some teachers would have you use just compass. Some teachers would allow you to use the program online, and some teachers would or would not let you use a ruler. So every teacher is different. Make sure to talk to yours. Dilations. This is just the definition, the explanation of it. So if you have a dilation right here, this is important. A dilation, and then the N is like the size, 1/2, twice as big, 3 times, and then that C is the point of dilation. So dilation, some amount from some point. That's a transformation, and it is not a rigid transformation. So you think about it, a rigid transformation is like rotation, reflection. Those do not change the shape. This is not rigid anymore. It actually changes the shape bigger and smaller. And if it's a dilation greater than 1, it's going to get bigger or enlarged. If it's a dilation between 0 and 1, so like a fraction less than 1, then it's a reduction. There's no negative dilations. Analyzing dilation. So we're going to look at this problem right away. Find the original pre-image and then find the changed image or image. So it's pre-image and image. So ABCD, this is the pre-image because there's no primes. And this one's the image. So let's walk through this solution. And I love it because it actually, again, goes through it step by step with you. So they are rectangles, which means all 4 of the original angles are 90, all 4 of the new angles are 90. And then it goes through and compares the side lengths. So you're just going to count. So I usually take the new image first. When you write a ratio, there's lots of different ways you can do it, but I'm going to say new, as in new measurement, over the original or the old measurement and that's my ratio. So that would be like my scale factor. And oftentimes the scale factor is referred to as R. Sometimes it's N, like it was on the last screen, but sometimes it's R. So just be aware, look for that scale factor, and that scale factor is the new over the original or the old, whatever you decide. So let's look at this. All right, so it says it's comparing the AB to the A prime B prime. So they just counted. AD is 2, AD prime 1, 2, 3, 4, 5, 6. And again, they just went through and counted everything. And look at these ratios. They took the new, right there, A prime B prime, over the original or the old AB. And they reduced the fraction if possible. And it's 3. The scale factor is 3. And sometimes you can find it really quick and you don't need to do all this setup, but this is the right setup because they're just going to get more difficult from this. So the ratios are all equal. Notice they're all 3. Since they're all 3, it is a definite scale factor or a dilation. If even one of them is wrong, it's not. It does not work unless all of the measurements increase or decrease the exact same ratio. So here says, here's a rectangle with a dilation from center P. So look at where the center is. How are the side lengths and angle measures of the two related? So first of all, look at angle measures. If the angle measures changed at all, it's not a dilation. Angles have to be preserved. So angles do not change. So I'm looking at all these. Since we have a graph, we can tell that they're all 90 degrees on the pre-image and the image. All of them are 90. And then we look at the side lengths. So I'm going to count 1, 2, 3, 4, 5, 6. And I'll just go ahead and label it 6. 6. And I'm going to count this 2. This is 1. This is 3. And it's a rectangle. So I'm going to just keep measuring 1 and 2. So it says, how are the side lengths and the angle measures of the two related? So first of all, I already said the angles are all the same. They have not changed. But the side lengths, and this is where you can take that ratio or scale factor and put the new, and just for simplicity reasons, we're going to say old or original. So my new measurement is, let's say 2. Notice I'm just taking one measurement and I'm going to compare it to the corresponding parts. It's both the XY and the XY prime. So I'm going to say my new is 2. My original or old is 6. I'm going to reduce that and I get 1/3. As long as it's 1/3 for every corresponding set of points, set of sides, then you know it is a dilation. Okay, example 3 says, find the scale factor. So scale factor, and I'm going to do new to old or original, whatever you prefer. So my new shape, look for those prime, those tick marks. Here's my new shape, 18. So I have scale factor equals 18. Take the corresponding part. And honestly, these are the only parts we've got. So good thing we have one set of corresponding parts. And I reduce this. To reduce this, think of it as just a fraction. What number goes into 18 and 12 that I can divide by? So if you're not sure, say, I think it's a 2. So I'm going to go by 2. And then I get, okay, well, that's 9 and 6. So I'm like, wait, they both have 3. So I'm going to divide again. And it's okay if you don't pick the greatest common factor at first. It's fine. So 9 divided by 3 is 3. 6 divided by 3 is 2. So I'm like, okay, my scale factor is 3/2. This is example 3, but try it. So it says, is this a dilation or enlargement? Look for the primes. So I look at these and I go, okay, these are primes, the A prime, B prime, C prime, and it obviously got smaller, so it's a reduction. It reduced in size. And then what is the scale factor? That's when I get my pen, and I'm going to say my scale factor equals, notice we're getting it a little bit more simple each time, new to old, or new to original. My new, got a 1, a 2, and I can do the Pythagorean theorem to figure out this length right here. I might not have to. Let's see if I can figure it out. 2, and this is 1, 2, 3, 4. So let's try these two sides. I'm going to have my new shape is 2 to 4. I'm taking these and comparing them. And then I'm like, okay, well, that's 1/2. Let's try one more, new to original. And let's try these ones. Let's see, my new is 1. Oh yeah, they both are. And by doing the Pythagorean theorem, I could compare the C to B and C prime to B prime. I can compare those if I want to as well. But it looks like the scale factor is 1/2. Here's an example that uses a graph. So you're doing dilations on a graph. So it says, here's the notation, dilate with a scale factor of 3. Notice there's no point of dilation. And if that doesn't happen, it means it's going from the origin. So if there's no like D with a comma, like a letter, and then the 3, then it means the origin on a graph. So from the origin, I need to dilate this figure 3 times as big, a scale factor of 3. So let's go through this step by step. So it says it needs to be 3 times further away. I love when it's dilated from the origin because it's easier math and more kids understand it. So you take the ordered pairs, and you would have to figure out what the original ordered pairs are of A, B, and C. Okay, you just figure each of those out and you write them down. Then each component, like the X and the Y, you multiply by 3. So it gives examples. So instead of 2 and -1, notice it's 2 and -1 each times 3. And then you get the new point. A prime is 6, -3. So you literally multiply each point by the scale factor, only if the dilation is from the origin. And it says, okay, here's the, and ends up as here's the new points or the points of the image. Perfect example, dilation from the center. There's no point, so it's dilation of 1/4. So find those ordered pairs, and I would do it in a certain way. So I label the ordered pairs right on the picture. So this looks like -4, 0, and this is 8. Let me count over, 4. And this right here looks like 12, -4. There we go. Now, if we're doing 1/4, you're going to take each of these ordered pairs, each component of the ordered pair, and multiply by 1/4 or divide by 4, and you'll get the same answer. So I want you to figure that out on your own, but take each component dividing by 4 or multiplying by 1/4. Okay, example 5. This is one of the harder problems, and to be honest, if you go through step by step, just like you did the other problems, it will be okay. So let's start by like labeling the vertices like we did on the other ones, dilating from the origin. Even though this is a scale factor of 1/2, dilating from point R. Okay, so point R, it looks like it's a -2, 7. Point S, I think that's a 4, and again, it would be 7. Point T, 4, -1. I want to make sure that's a -1 right there. -1 is not a 4. And then this one looks like Q is a -2, -1. Okay, so those both are -1s. Not that first one looks like a 4. So what are the solutions? You have to figure out in a different way because we're not going from the origin again. Sorry. You need to figure out the distances between the 2 points. And just because we're running out of room, I'm going to do this on the inside. Okay, the distance or difference between -1 and 7 is a distance of 8. And if you weren't sure, you can count that. The distance or difference between 4 and -2 is 6. And again, you can count that if you're not sure. So I need to take this scale factor and basically cut 8 in half, getting closer to point R. And then I need to take 6, cut that in half, and get closer to point R. The book has the solution. It explains what I just explained. And then it says, find the difference. So right here, where it's saying like, okay, 0 to -8 and 6, it's a difference of 8. It's going downward 8, and it's going to the right 6 from that point R. And then it's taking those distances and cutting them in half. So half of 8 is 4. And the reason why they use negative because it's going downward, and they need to bring it back up. And the reason why they're using a positive 6, cut that in half, which is 3, is because it's going to the right, or the positive distance, which is to the right. So, and then it adds it to the originals. These I didn't have on there yet, but this is what you do. Notice when I'm going vertically, my X's are not changing, just my Y's. When I'm going horizontally, my Y's are not changing, just my X's. And it goes through step by step. Let me show you some more. Here is one of the visuals that you can see. So it cut each of these points, S, halfway from S to R is S prime, halfway to Q is Q prime, and then they connect it by creating this center R using a line that goes from R to point T. and they bring those where S comes together and Q comes together and meets right at T. Let's look at the next part of the solution. It says, here are the new vertices, and it wrote the notation, dilation, 1/2 scale factor from point R. That's a hard problem. Example 5 is similar. Example 5, try it. It says a dilation from ABC is shown. So it gives you the actual original, the pre-image and the image. What is the center of dilation? So this one takes what we just went over and it's just saying, hey, find it. Where is the point of dilation or center in which it enlarged? Try to figure that out on your own. Example 6 is this an application problem. I love this problem because this is reality. This is where we use scale factors. It says a blueprint of a new library uses a scale factor of 1/50. Mr. Ayers measures the reading space in the blueprint to find the actual measurements and area so we can order the furniture. So you're not only finding the measurements, you're finding the area. So it is a rectangle. It might even be a square. It's hard to tell right now. Nope, it looks like a rectangle. Just because one side length is different. So it's a rectangle. To find the area is going to be length times width or base times height. So let's just find the dimensions first of all. So we're going to use the scale factor of 1/50, which means in case the blueprint is 1, for every 1, there's 50 of the actual drawing. So it's not new to original. It's like saying the scale factor, and I can write this on here. This 1 is representing the blueprint, and the 50 is representing the actual. And you can say actual, and you could say blueprint, however you want to write it. But just make sure you keep whatever your ratio is, like new to old, blueprint to actual, small to big. Make sure you're consistent in the entire problem. So we'll leave that with blueprint to actual for now. Okay, if I slide down on this problem, it tells you right here, oops, trying to get that out of the way. It shows you that it has this scale factor, 1/50, and then it has 12 over y. So think about what I just said with the ratios. If I have blueprint to actual, I'm going to set that equal to blueprint to actual. So not only do I have a ratio, now I have a proportion where I'm actually going to solve things. So ratio is just one comparison, like a fraction. Proportion is when you take 2 of those comparisons and set them equal. So it looks like a fraction equal to a fraction. So I have 1 measurement on the blueprint equals 50 on actual. 12, as in 12 inches right here, up there at the top. I need to figure out what the actual is. Okay? They also did the same thing over here. 1/50, blueprint to actual, equals blueprint, that 14 inches right here on the side, which I just circled and messed up, and you're going to try to find the actual measurement. So if you know how to do that, cross multiply and solve for x and y. If you don't, there actually are the steps here. The problem works it out for you, and then it tells you. So if x is 700, it means that the reading space is 700 centimeters, which when you measure a room, you don't usually go in centimeters. So it's 7 meters. And 600 centimeters, which is 6 meters. So that's how big the reading space is. There are a couple more problems based on this same application problem. Go ahead and try those on your own. Ask for help if you need help, but they're still related to that same blueprint idea. And here's another one that has a blueprint idea, but the scale factor has changed. Dilation is a transformation that changes the figure as it moves. So it is definitely not rigid. Rigid means it doesn't move at all. It changes location, but the shape doesn't change itself. This one actually changes the shape. Okay, so the shape has movement and it changes. So the angles are preserved. Notice how all these angles are marked. So I love how they mark these right here. And the angles are marked. Angles do not change on a dilation. Okay, but the size changes, and it goes through and shows you how. It gives you the notation down here at the bottom, and basically it means a dilation can increase in size from any given point or center. If the scale factor is greater than 1, it's going to be an enlargement. If the scale factor is between 0 and 1, it's going to be a decrease in size. I hope that helps.